Hello everyone, my name's Imane. Welcome back to my YouTube channel. Today we're going to tackle a practice problem set that relates to our lecture on part 2 of aldehydes and ketones. Let's go ahead and get started with problem number 1. Problem number 1 says, what is the product of the reaction below? In this reaction, we notice that we have an aldehyde. The aldehyde that's shown here is ethanol, which has 2 carbon atoms, one for the carbonyl carbon, and the other carbon is part of a methyl group. Since this is an aldehyde, that carbonyl carbon also has a hydrogen attached to it. Then we have an alcohol. The alcohol is 1-propanol. This is a 3-carbon primary alcohol. Since we're reacting one equivalent of aldehyde with one equivalent of alcohol, the product formed is going to be a hemiacetal, which is the result of a nucleophilic addition of an alcohol to an aldehyde. In the mechanism, the nucleophilic oxygen of 1-propanol attacks the electrophilic carbonyl carbon of ethanol. This breaks the pi bond of the carbonyl, and the electrons are going to be pushed onto the oxygen. The oxygen from the carbonyl is then protonated, and no groups are lost because hemiacetal formation does not involve a leaving group. So the resulting product is going to have a central carbon that comes from the carbonyl carbon. It will be attached to an alcohol group. The carbonyl turns into this alcohol group. It remains attached to a hydrogen and to a methyl group. The only difference is that the 4th attachment to that carbon is going to be this part of our alcohol. So OCH2, CH2, CH3. This is what's called a proproxy group. It comes from the alcohol. Looking at this, the option that best matches is going to be answer choice D. Problem 2 says, the reaction below is an example of blank. We're given a reversible reaction where a compound with a carbonyl group, specifically this is an aldehyde, it's in equilibrium with a compound that has both an alcohol group and a carbon-carbon double bond. This transformation involves the migration of a proton and a shift in the position of a double bond. This is a textbook example of tautomerization, specifically Keto-enol tautomerization. In this process, the compound interconverts between 2 isomer forms, a keto form, which contains a carbon-oxygen double bond, and an enol form, which contains an alkene and a hydroxyl group on the same carbon. Therefore, the correct answer for problem 2 is B. Problem 3 says, which of the following reactants would produce the compound below? So we are asked which pair of reactants would produce the compound shown. This is a beta-hydroxyaldehyde, meaning this is an aldol addition reaction. In aldol reactions, one carbonyl compound forms an enolate ion under basic conditions. This enolate then attacks the carbonyl carbon of another molecule, forming a new carbon-carbon bond. The easiest way to solve this problem and figure out what 2 reactants can produce this product is by creating a little cut in between the alpha and beta carbons with respect to the carbonyl group. So when we create this little cut, what's on the right side is our first reactant. So we notice it's an aldehyde. That means the carbonyl carbon's attached to a hydrogen. And the other group it's attached to is an ethyl group. So if we were to write the molecular formula for this first reactant, it's going to be CH3, CH2, CHO. Now, what about the other side? So the other side is going to be our second reactant with a few modifications. We're going to convert this alcohol group to a carbonyl. And then where we created this little cut, that indicates that that carbonyl carbon is attached to a hydrogen. So our second reactant looks something like this. It looks exactly like our first reactant. So CH3, CH2, CHO. Both of our reactants, the first and second, are exactly the same. They are propanol. So both fragments come from the same aldehyde, and that suggests a mixed aldol condensation where one molecule of propanol forms an enolate and then it attacks the carbonyl of another. The correct answer here is going to be D. Problem 4 says, why does the equilibrium between keto and enol tautomers lie far to the keto side? Let's work through each statement carefully. Statement 1 says the keto form is more thermodynamically stable. This is a correct statement. In most simple carbonyl compounds, the keto form is more stable than the enol form due to the strength of the carbon-oxygen double bond in the carbonyl. The carbonyl bond is stronger and lower in energy than the carbon-carbon double bond in the enol, making the keto form more thermodynamically favorable. This is the key reason why the equilibrium lies far to the keto side. Statement 2 says the enol form is lower in energy. This is incorrect. In fact, the enol form is higher in energy than the keto form in most cases, which is exactly why it's less favored at equilibrium. Finally, statement 3 says the enol form is more thermodynamically stable. This is also incorrect. The enol form is generally less thermodynamically stable than the keto form. There are some exceptions in very specific cases, but those are not typical. So the only statement that's correct is statement 1. So 4 is A. Problem 5 says the aldol condensation is an example of which reaction types. First, the aldol condensation begins when a base removes an acidic alpha hydrogen from an aldehyde or ketone. This forms an enolate, which is a strong nucleophile. This enolate then performs a nucleophilic addition by attacking the carbonyl carbon of another aldehyde or ketone molecule. This is the key carbon-carbon bond-forming step and is characteristic of nucleophilic addition reactions. So statement 3 is correct. After the addition, we get a beta-hydroxy carbonyl compound called an aldol. Under heating conditions, this intermediate undergoes dehydration, meaning a molecule of water is eliminated and a new double bond forms between the alpha and beta carbons. This elimination of water gives us an alpha-beta unsaturated carbonyl compound. So statement 1, dehydration, is also correct. Now, for statement 2, cleavage, this does not happen during a standard aldol condensation. No bond is broken between atoms in a way that produces two separate fragments, which is what this statement is referring to. So statement 2 is incorrect. Only 1 and 3 are true. Therefore, the correct answer for problem 5 is B. Problem 6 says, which of the hydrogens in the following molecule is the most acidic? To determine which hydrogen in the molecule is the most acidic, we need to evaluate the stability of the conjugate base that would result from deprotonating each position. Let's go through each option. Hydrogen A is part of an alkene. sp2 hybridized hydrogens are slightly more acidic than sp3. Let's keep that in mind as we work through the other options. Hydrogen B is an alpha hydrogen that's actually located between two carbonyl groups. This position is highly acidic because the removal of this hydrogen forms a carboanion that is resonance stabilized by both adjacent carbonyls. The negative charge can delocalize onto both oxygens through resonance, and that greatly stabilizes the conjugate base. Hydrogen C is also an alpha hydrogen, but it's only adjacent to one carbonyl group. It's more acidic than A, but it's less acidic than B due to having less resonance stabilization. Finally, we have hydrogen D. It's attached to an sp3 carbon, so it's the least acidic of the hydrogens we've explored. If we were to rank them from least to most acidic, it would be hydrogen D is the least acidic, then A is a little bit more acidic, then C, and then finally B. Hydrogen B is the most acidic hydrogen, so the correct answer for problem 6 is B. Problem 7 says, when reacted with ammonia at 200 degrees Celsius, which enolate of a carbonyl-containing compound would predominate? To solve this problem, we really need to think about the conditions that favor the formation of kinetic versus thermodynamic enolates. The kinetic enolate forms more quickly. It's the product of deprotonation at the less substituted alpha carbon because that hydrogen is more accessible. Formation of the kinetic enolate is favored by low temperatures and strong bulky bases and irreversible conditions. On the other hand, the thermodynamic enolate is the more stable enolate overall. It forms by deprotonation at the more substituted alpha carbon, where the resulting double bond is more substituted and better stabilized. Formation of the thermodynamic enolate is favored under high temperatures and weaker or smaller bases and reversible conditions that allow equilibrium to be established. In this problem, the reaction is carried out at 200 degrees Celsius. This is a high temperature, and with ammonia, which is a relatively weak base. So these conditions clearly favor thermodynamic control. The system has enough energy to reach the more stable product, and the reaction can equilibrate over time. Therefore, the correct answer here is B, thermodynamic enolate. Problem 8 says, which of the following compounds would be most reactive towards a nucleophile? To determine which compound is most reactive towards a nucleophile, we need to focus on the electrophilicity of the carbonyl carbon. That is, how electron deficient it is and how accessible it is for attack. Let's break down each answer choice. A says pentanal. This is an aldehyde. Aldehydes have one hydrogen and one alkyl group attached to the carbonyl carbon. This makes the carbonyl carbon more exposed and more electron deficient, and that makes it highly susceptible to nucleophilic attack. Then B says 3-pentanoate. This is going to be a ketone, so the carbonyl carbon is attached to two alkyl groups. These electron-donating alkyl groups are going to stabilize the partial positive charge on the carbonyl carbon, and that's going to make it less electrophilic than an aldehyde. Plus, there's more steric hindrance that reduces accessibility. The same goes for D, which is another ketone. C is pentane. This is an alkane. It has no carbonyl group and no electrophilic center at all, so it's not going to be reactive towards nucleophiles. So out of all of these options, pentanal is the most reactive towards nucleophiles because it has a highly electrophilic carbonyl carbon and minimal steric hindrance. So A is the correct answer. Problem 9 says alpha hydrogens of a ketone are acidic due to blink. Let's analyze each statement. Statement 1 says resonance stabilization. This is correct. When an alpha hydrogen is removed, the resulting negative charge on the alpha carbon can delocalize through resonance with the adjacent carbonyl group. This forms an enolate ion where the negative charge is partially shared with the more electronegative oxygen atom. This delocalization stabilizes the conjugate base and it makes the alpha hydrogen more acidic. Statement 2 says the electron withdrawing properties of alkyl groups. This is incorrect. Alkyl groups are actually electron donating through inductive effects, not withdrawing. Their presence can slightly destabilize a negative charge on the alpha carbon, which would reduce acidity, not increase it. Statement 3 says the electronegative carbonyl oxygen. This is correct. The carbonyl oxygen is highly electronegative, and through its inductive effect, it pulls electron density away from the alpha carbon. This helps stabilize the developing negative charge during deprotonation, and that contributes to the acidity of the alpha hydrogens. So only statements 1 and 3 are valid explanations for the acidity of alpha hydrogens in ketones. The correct answer is B. Problem 10 says, which of the following is considered a tautomer of the imine functional group? Tautomers are isomers that readily interconvert by the movement of a proton and a shift of a double bond, and they exist in a dynamic equilibrium. When we're talking about imines, the most relevant tautomer relationship is with enamines. An imine is a compound featuring a carbon-nitrogen double bond, usually formed by the condensation of a primary amine with a carbonyl compound. In contrast, an enamine has a nitrogen atom that's bonded to a carbon that is also part of a carbon-carbon double bond. Under acidic or basic conditions, an imine can undergo tautomerization to form an enamine. This process involves shifting a proton from the alpha carbon to the nitrogen and moving the double bond from the carbon-nitrogen double bond to a carbon-carbon double bond. So structurally, imines and enamines differ only in the location of a double bond and the proton, and that makes them tautomers of each other. Therefore, the correct answer for problem 10 is C. Problem 11 says, when succinaldehyde is treated with LDA, it blank. LDA is a strong, non-nucleophilic base that's commonly used to generate enolates by removing an acidic alpha hydrogen from carbonyl-containing compounds. Succinaldehyde contains 2 aldehyde groups, and the hydrogen atoms on the alpha carbons are relatively acidic. When treated with LDA, one of those alpha hydrogens is abstracted, and that forms a carbanion at the carbon. This carbanion is resonance stabilized by the adjacent carbonyl group, and that gives rise to an enolate ion. Enolates are significantly more nucleophilic than their parent carbonyl compounds because they have a negatively charged carbon with available electron density. And this makes them highly reactive towards electrophiles, especially in carbon-carbon bond-forming reactions. Now let's evaluate these statements. Statement 1 says it becomes more nucleophilic. This is true. The formation of the enolate increases the compound's nucleophilicity. Statement 2 says it becomes less nucleophilic. This is false. The opposite is true. The compound becomes more nucleophilic after deprotonation. Then finally, statement 3 says it generates a carbanion, and this is true. The base takes away an alpha hydrogen, and that forms a negatively charged carbanion stabilized by resonance with the carbonyl. So since statements 1 and 3 are true, the correct answer for problem 11 is C. Problem 12 says, which of the following best describes the final product of an aldol condensation? An aldol condensation occurs when an enolate ion attacks another carbonyl compound to form a beta-hydroxy carbonyl compound known as an aldol. However, that's only the initial product. Under heated or acidic basic conditions, the aldol undergoes dehydration, meaning a molecule of water is eliminated. This elimination leads to the formation of a double bond between the alpha and beta carbons. The result is a molecule containing a carbon-carbon double bond conjugated with a carbonyl group. This structure is called an alpha-beta unsaturated carbonyl. Therefore, the correct answer for problem 12 is C. Problem 13 says, when benzaldehyde is reacted with acetone, which will act as the nucleophile? Benzaldehyde is an aldehyde attached to an aromatic ring, and acetone is a ketone with two methyl groups on either side of the carbonyl. This structural difference is key to answering this question. Under basic conditions, the most important factor in determining nucleophilicity is whether a compound has alpha hydrogens. These are hydrogens on the carbon adjacent to the carbonyl. These alpha hydrogens can be deprotonated by a strong base, and that forms an enolate ion which acts as a nucleophile. If we look at benzaldehyde, it lacks an alpha hydrogen because the carbon next to the carbonyl is part of an aromatic ring. There's no available hydrogens to remove. Acetone, however, has alpha hydrogens on both sides of the carbonyl group. So in the presence of a strong base, one of these hydrogens can be removed, and that generates an enolate ion. This enolate is nucleophilic, and it attacks the electrophilic carbonyl carbon of benzaldehyde in an aldol type reaction. So the carbonyl of benzaldehyde is highly electrophilic, and that makes it an ideal target for nucleophilic attack. So although both molecules contain carbonyl groups, only acetone can form an enolate, and therefore only acetone acts as the nucleophile. All right, so the correct answer here is going to be D. Acetone after reaction with strong base. Problem 14 says 3-hydroxybutanal can be formed by the reaction of blank. The first thing we want to do for this question is go ahead and draw out 3-hydroxybutanal. The name also tells us a lot. It's a beta-hydroxyaldehyde, and that is a characteristic product of aldol condensation. The reaction is stopped after aldol formation before dehydration because the product is not an alpha-beta unsaturated carbonyl. So this means that after the aldol is formed using strong base, the reaction has to be halted by the addition of an acid. With this information in mind, we can proceed to answer this problem using the same little trick we implemented in problem 3. The easiest way to solve this and figure out what two reactants can produce this product is by doing a little cut in between the alpha and beta carbons with respect to the carbonyl group. On one side, on the right side right here, we have our first reactant. We have our carbonyl carbon that's attached to a hydrogen and to a methyl group. This is ethanol. Then on the other side of our little cut, we're going to convert the alcohol to a carbonyl, and this carbonyl is attached to a hydrogen on the right side. So when we draw this properly, we have our carbonyl group. It's attached to a hydrogen and to a methyl group. So again, reactant 2 looks exactly like reactant 1. We need ethanol in base, then in acid, for us to form 3-hydroxybutanal. So 14 is B. Now we can move into our last and final problem. Problem 15 says the catalytic production of dihydroxyacetone and glyceraldehyde 3-phosphate from a fructose-based compound is what type of reaction? The key to this problem is not to get lost in drawing these structures. This falls outside the scope of the MCAT. However, what we can recognize from the nomenclature is that we are forming a ketone and an aldehyde from a single molecule. Both products contain carbonyl groups, and the transformation involves breaking a carbon-carbon bond within a single molecule to yield these two products. This is characteristic of a retro-aldol reaction, which is the reverse of an aldol condensation. So the correct answer for problem 15 is going to be B. And with that, we've completed this practice problem set. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.